Number 47. This is chapter 8, number 47. Okay. And that's on page 266. All right. Okay, so we got a block of mass A with 2 kilograms and block of mass B of 6 kilograms move on a frictionless horizontal surface. Initially, block B is at rest. All right, so let's draw the initial. This is block A, and this is block B. All right, and so block A, mass of A is 2 kilograms, and mass of B is 6 kilograms, right? Okay. And so the initial velocity of B is 0 meters per second. It's important to write that down. Okay. Is at rest, and block A is moving toward it at 2 meters per second. So block A is moving this way, and the velocity of A is 2 meters per second. And by the way, we're going to make that positive since it's moving to the right. Okay. Now let me ask you something. Let's just go ahead and get this out of the way. What would be the kinetic energy of block B initially? 0. So let's go ahead and write that down too. Kinetic energy of B initial is 0 joules, orange juice, okay? OJ, all right? Okay? All right. Let's go ahead and get it out of the way. All right. The blocks are, let's see, is at rest, moving 2 meters per second. All right, the blocks are equipped with an ideal spring bumpers, as in example 8.10, section 8.4. The collision is head-on, so all motion before and after the collision is along a straight line. So it should be what kind of collision? Elastic or inelastic? So they have bumpers, and let's just put a spring bumper there and a spring bumper. Okay. And so they do what? They collide. Okay. Spring bumper. Right. So this is after collision. Before collision. All right. And so since they have elastic bumpers, they're going to do like what happened with the magnets in lab. They're going to do what? Bounce apart, aren't they? So it's going to be an elastic collision. Is that correct? Would that be a safe assumption? Sure it would. Okay. So this is an elastic collision, right? And what do we know about elastic collisions? Well, first of all, collisions, what happens to momentum? Momentum is always what? Conserved. In an elastic collision, what else is conserved? Kinetic energy. Very good. All right. Okay. All right, let's see here. The collision is head-on, so all the motion before and after the collision is along a straight line. Find the maximum energy storage in the spring bumpers and the velocity of each block at that time. Okay? Okay? All right, so we have spring bumpers. What kind of a energy is that? A spring is what kind of energy? Is it kinetic or potential? It is potential, isn't it? Okay. All right. Do you remember that kinetic energy, that conservation of energy equation? The work kinetic energy theorem? And the conservation of energy equation where we said what? That K initial plus U initial is equal to what? K final plus U final, absolutely. Right? Okay. Now you can't forget that you've got 2 objects here, right? So each one has potential energy and each one has kinetic energy. So there's a K initial A and K initial B and U initial A and U initial B, correct? And likewise on the finals, right? That makes sense? It have to, okay? All right, so we want to find what? We want to find the potential energy of what? All right. We got to find for what on the first one? Find the maximum energy stored in the spring bumpers. Okay. Maximum energy stored. Okay. All right. Now, let me make sure I've read this right. All right. Both boxes are equipped with ideal spring bumpers. Okay. The collision is head on, so all motion before and after the collision is along a straight line. Okay. All right, section 8.4. Let me make sure I'm looking at the diagram right too. Okay. Figure what? What figure was that? 8 what? 10. Yeah. Examples 8.10. Excuse me. Example 8.10. Yeah, there it is. Okay, yeah. All right, so I did have it drawn right. I didn't put my arrows in, though, did I? Okay. All right, so we're missing something here, aren't we? What are the final velocities? It didn't give us the final velocities, did it? Now, we know that B's initial energy is 0 because it's sitting at rest. All right. We also know that momentum before is equal to momentum after, right? Okay. So I want to find now the final velocity of the block or both blocks. Okay. All right. Okay. So, because we have initial velocity, all right, we have initial velocity, but we don't have final velocity. So let's find final velocity. So we know mv initial is equal to what? mv final, right? Okay. All right, so let's plug everything we know in. Well, we know that this block is motionless to start with. B is motionless. So actually the only one that has any momentum to start with is what? A, right? So we've got 2 kilograms times 2 meters per second is equal to, now, let's look at the final velocity of both blocks combined. So let's add both masses together, and that's going to be 2 plus 6 kilograms V final, right? Now again, I'm getting it from that right there. And so I get a final velocity of both blocks should equal what? Oh, where did I have it written down? I have it written down somewhere. Yeah, there it is. Okay. So we should get a final velocity of 0.5 meters per second. Okay. All right. All right, now let's go to this equation. And you say, well, why did I do that? Well, look, y'all, we've got to find a final velocity. We've got to find a final velocity. Now we can take this equation. Now, if you remember, K initial of K initial B is 0. So this equation becomes what? It becomes Ka initial. And by the way, is there any potential energy initially? There would be potential energy. Is there any potential energy for A, though? Because it's moving. So A potential energy, so let's write that down too. So we've already written this down. KB is 0. What about UA? UA is 0. UA initial is 0. So all we have for A is kinetic energy, right? All right. So then our equation's going to look like what? It's going to look like this right here. Now, we're looking for what? We're looking for the potential energy of B and the kinetic energy of both, right? Kinetic energy of A and B, right? All right. So let's plug everything in. So we got what? 1/2 times what? 2 kilograms times 2 meters per second is equal to, well, UB we don't know. That's unknown. That's what we're looking for. UB is unknown. Plus 1/2, and I'm going to add both masses. I can do that. 8 kilograms times our velocity, 0.5 meters per second. And we should get a UB of what? 3 joules. So that would be the elastic potential energy after the collision, or at the time of the collision, excuse me, at the time of the collision. Because that's, and this question's a little bit, the way they worded it, it didn't word it clearly. They're wanting to find, it says at that time. Well, at what time? They're actually talking about the time of collision. In other words, when they come together, you got to realize, and that's why I added both masses right there. It's at the point they come together. It's at the point of collision. It's right here. It's not here. It's not here. It's right here. Okay? That's what we're looking for. So it's a little bit that, if I'd have written that question, I'd try to word it a little bit better, and they didn't do a good job wording it. Okay? So the potential energy is 3 joules. Okay? Oh, yes, thank you, sorry. I knew I was leaving something off. I was thinking about momentum, sorry. Thank you, sorry about that. All right, now let's look at part B. This problem's a little bit challenging. It's pretty challenging. Okay, find the velocity of each block after they moved apart, okay? So we want to find the velocity after they move apart. Well, actually, what it becomes is a ratio. And we go to our equation, let's see, that's on page, where are those equations at? Let's find them real quick. Because I want to just tell you so you can look at it, and I'm going to write it down. Elastic collisions, yeah. It actually becomes, yeah. Okay. Yeah, there we go. It becomes this equation right here. VA final is equal to M of A minus M of B over M of A plus M of B times the velocity of A initial. Okay? And that's on page 252. Okay? Equation 8.24. All right? All right, so let's plug in. And we have to do two different calculations. This is the first one. So we got 2 minus 6 over what? 2 plus 6 times what? 2 meters per second. And that comes out to be a -1. -1 meters per second. Right? Now let's do VB final. And the VB final is this equation right here. This is on the same page, 2MA over MA plus MB times what? VA1. VA initial. Okay? And so let's plug it in. And that is equation 8.25. Same page. All right? Now, we could also solve this with that derivation I sent you. We could also do it that way and then go back and substitute in. We could do it that way too. All right? Might be a little, I don't know if it's really any easier. It's going to be about the same amount of work. Okay, it's kind of involved. That's the problem with elastic collisions. It's when you have, especially when two objects are moving. Now when one's at rest, it's easier, but when both are moving at initial, it becomes much more complicated. And that derivation I sent you a week or so ago is how we solve it when both are moving initially. Okay, all right. But we could also use it for this too. All right. If one of your terms goes away because it's 0 initially. All right. Okay, so let's plug everything in. So we got 2 times what? 2 kg over what? 2 plus 6 times 2 meters per second. And we get an answer of what? 1 meter per second. Wow. So notice they both had the same velocity, magnitude, but notice the directions were opposite. Okay? Okay. So notice how the velocity was what? The velocity of B was half the velocity of A initially, right? Initially A was what? 2 meters per second? So B takes on the velocity, half the velocity of A. Finally. And it's moving in the same direction. This is positive. This is moving to the right. This one right here is moving to the left, right? So go back to our drawing. Go back right here. 1 meter per second, -1 meter per second. Okay? You could do this with the PhET simulation I showed you the other day, and you could play around with it and punch in the values and do it, and you should get the same results. Okay? All right. That one's kind of involved. All right. It wasn't worded quite the way I think it should have been worded, but again, if I word it, you know I'm going to make it clear, a little bit more clear than that. Okay. I'm trying to remember on your exam, you will have an inelastic calculation. I'm pretty sure you'll have to do an elastic calculation too, and more than likely when it's at rest. But I may only ask you the velocity of one instead of both. Okay. So make sure you have, and I gave you those equations, make sure you have those two equations, okay?